Okay, so last chapter. The plan today is basically to cover, I think it's 7.2, 7.3, and then the rest in the next set of lectures. I have put it up in case I have extra time. So clearly, when you're dealing with boundary layers, one of the things that you worry about is drag force. And we have gone through a great deal of effort looking at drag and how to define it. And ultimately, the goal in this chapter is to give you a set of empirical values or approaches so that you can solve them a bit easier than this. But let's sort of keep marching through this. And here we have von Karman's integral relation. And again, 1921, 104 years later, we're still using it. You have what you're used to now, which is a boundary layer. You have an approaching flow field. It is affected by the wall. And that effect, that viscous effect, starts to be defined by this term delta. And delta is that boundary layer thickness, which we've defined as being the point where you reach 99% of the free stream velocity. And I'm going to give you the definition of momentum thickness in a second. But first, we'll use it in terms of how we define drag. And so drag is going to be related to the width of the plate, B, the free stream velocity, and the density of the fluid you're using, multiplied by theta. So you have theta there, which is your momentum thickness. If you differentiate, you can get the local wall shear, which is just going to be d dx b tau w, and you have u squared d theta dx rho. Go ahead. Good question. Next slide. And the problem with defining momentum thickness is that I can't really define it easily right away. Maybe I should flip these around. Maybe I should flip them around. So anyways, I have momentum thickness, which is going to be related to boundary layer thickness. So you integrate from 0 to delta, and you do u over u infinity times 1 minus u over u infinity dy. And for a laminar profile, you have u over u, which has a shape which is 2 times y over delta squared. If you do this and you integrate, you end up with a momentum thickness, which is delta, which is essentially the effect of the boundary layer on momentum on across the flow. So essentially the deficit of momentum that you have. So it's the difference between what you would get if you have a free stream and what you would get if you just, once you put this into the flow, so the wall or the obstacle. So this is about 10% off of the exact Blasius solution, 5 over square roots of Reynolds numbers x, based on x. And remember, again, one of the defining characteristics of boundary layers is they grow infinitely. And so their value starts at 0 right at the beginning, but they can grow forever. And so Reynolds number based on x means that it will change with time. Another value that we tend to use is displacement thickness, and it's the distance the outer flow is pushed away from the wall. And so it's going to be just part of that momentum thickness term, and it's the 1 minus u over u infinity term dy. Again, integrated from delta, and for a laminar flat plate, I've decided to solve it. It's about 1/3 of the boundary layer thickness. So you can do a number of different approaches, but it's kind of interesting to just look at a linear profile. And a linear profile for u over u infinity would be just y over delta. And so for y less than delta, so within the boundary layer. And we have the boundary layer thickness then, which is just going to be, or sorry, the momentum thickness, which is going to be u over u infinity times the quantity 1 minus u over u infinity dy. And integrated from 0 to delta, that's the definition, substituting in this linear profile. So just assuming it goes from 0 linearly up to u infinity, you end up with y over delta 1 minus y over delta dy. And you can integrate that and if you do, you end up with delta, maybe I should write a better delta, over 6. And if you do that, then you can do du dy, y equals 0, which is mu u over delta for a Newtonian stress. And that, again, just going back all the way to chapter 1, and you've seen this before. For an integral equation, you end up with rho u squared, rho u infinity squared d delta dx. Any questions so far? So both of those are saying the same thing. So the Newtonian stress and the momentum thickness-based stress, the integral, has to be the same. And so we can separate out variables as we've done before. So you bring everything onto one side and everything else onto the other. Everything in terms of delta on the left. Everything in terms of x on the right. And you end up with delta squared over 2. It's approximately, or equals 6 mu x over rho u infinity. Delta equals 12 nu x over u. And out of that, you can resolve it, or rewrite it, as 3.46 over square root of Reynolds number x, which is very similar to the definition that we have for boundary layer thickness, which is going to be a function of 5 over square root of Reynolds x, which is the Blasius solution. And again, remember, we have the Blasius solution for a small set of equations, or a small set of conditions, but not bad for what it is. And it's not a lot of work in terms of figuring it out. Any questions on this one? Okay. Huh? If you replace the nibs on your Surface pen, everything works a lot better. Just sharing that useful bit of information. So what does a boundary layer do? So typically, and I'm going to solve these as English units, you can tell right away that one of the things that the boundary layer does is sort of shove fluid away from the wall. It creates sort of this layer where everything has got to move through. And so you have air that's entering a square duct 2 feet at 10 feet per second. The boundary layer displacement thickness grows as delta star equals 0.007 square root of x. The velocity of the inviscid core at x, or find the velocity of the inviscid core at x equals 100 feet. And what's happening is the boundary layer grows, and so it's essentially squeezing fluid, because you know that the fluid that came in at the beginning has to come out at the end. So the same amount of mass in 1 has to come out at 2, which means that all of that mass has to be accelerated in the center in order to maintain that flow. So we can say U in A in equals U core A effective. And what we're going to say is that that's 10 by 2 squared, 10 feet per second velocity. It's a square cross-section, 2 by 2. And on the right-hand side, we're going to use this concept, which I just told you, which is that this boundary layer or displacement thickness shoves fluid away. So it's the effective shoving of the fluid away. And in that case, the effective area is now going to be a core region that's going to be 2 feet minus 2 times the delta star. So you're essentially sort of looking at a smaller cross-sectional area. And you kind of see that when you look at the inviscid core and those dashed lines as you're going through. At x equals 100, delta star is 0.07 feet, and U core is equal to 10 times 4, 2 minus 0.14 squared, which equals 40 divided by 3.46, which is 11.56 feet per second. So essentially, what I've done is I've created a new area where all of the fluid's going through. Now, clearly, there is material that's going through the boundary layer component. I'm not considering it, but it's not as much as what had to be squeezed out in order to go through. Go ahead. This is a laminar profile, so it's pretty much the steady state average, or steady state flow. And so it will stay there. So what I'm looking at 100 feet is that. And the core flow is accelerated 15% by just this blockage. So we don't do very much about differential equations, but I do want to sort of touch on something that I think it's useful to sort of recognize. We did talk about the Navier-Stokes equation in chapter 4, and this chapter is actually really hard to teach without chapter 4, so I've got to think about what I'm doing on that one. But you can start out by saying, look, the layer is thin. The boundary layer thickness, delta, is much, much less than x. That's a reasonable assumption. No matter how far I go down the plate, the boundary layer thickness is going to be a small percentage of the downstream distance. So that's good. Streamwise velocity is dominant. Most cases, it's going to be dominated by the u direction velocity, not the transverse velocity. We're looking at two-dimensional flow largely. Gradients are huge. Delta u with respect to y is much, much greater than delta u with respect to x. And that one may be a little bit harder to see, but if I have a boundary layer, this is u infinity, this is 0, del u, del y changes very quickly. But even if you look at u infinity just a little bit downstream, del u infinity del x is not going to be very large. Or del u delta, sorry. So gradients are huge. Delta u with respect to y is going to be much, much larger than delta u with respect to x. And so you can show, and it's fun to do it, again, something for your weekends. The analysis will show delta p is equal to 0, and the outside pressure is is impacting things. So you end up with these equations. So delta U delta x plus delta V delta y, again, partials. Okay, partial U, partial x, partial V, partial y is equal to 0. And you get rid of all of the pressure terms. Pressure in a free stream, you can say delta P delta x is, or grad P grad x, okay, that's, is going to be 0. So you have the momentum terms, you have the mean momentum terms, and you have the shear stress. U is equal to constant, and del U del x is equal to 0, or du dx. And they can march downstream from the leading edge. And this is where you get that table we talked about in the previous lecture. So if you remember, no, not in your case, I sort of butchered that one. But if you looked at that table 1, I think it is from the previous lecture, you had eta and f prime. So this is where that came from. When looking at Blasius solutions for turbulent flows, you can't really do it. And what you end up doing is using power laws. And so the power law that ended up being the most popular is the 1/7 power law. U over U infinity is equal to y over delta to the 1/7. Using that equation and empirical data, you can find that delta over x is 0.16 Reynolds number to the x to the 1/7. So if you look at this graph over here, here's the Blasius solution, and that's for laminar flow. This is y over delta U over U infinity, and you'll notice it goes to a pretty high value relatively quickly. So the other lines are the turbulent lines. And so they change here 10 to the 7th, 10 to the 6th, 10 to the 5th. And this 7th root profile is actually pretty good because it does seem to fit reasonably well to that data. But again, that's something you've seen already, where when you have a turbulent flow, you have a lot more mixing going on in the center and a lot flatter profile. And if you remember the momentum correction factors, the mass correction factors that were introduced earlier, this is why. We looked at this before, but this is the same thing. It's essentially the closest thing we have to a Moody chart. So you can break it up into transition zones, laminar zones, and then turbulent zones. And again, one of the things that you should remember from your Moody diagram is that you have these flat points where you go to fully rough. And that dashed line shows you where that fully rough transition point occurs. You'll notice that it's there's a slight increase there, but it's not significant. The big change occurs to the left of that line. And unlike Moody, which is epsilon over d, this is L over epsilon. And so you have distances downstream. So 3 regimes, one which is hydraulically smooth. And again, if you're looking at a hydraulically smooth area, you have roughness elements there that may be some height. But the roughness elements are not going to be as thick as the boundary layer or the viscous layer. Transition, you start to see some poking through of these roughness elements. So they affect outside of the viscous sublayer. And because they do that, they are starting to change the flow. And that's when you get into these rough conditions. And then finally, you have fully rough, and drag is only dependent on Reynolds number and depends on the roughness factor L over epsilon. And so you have this relationship, 1.89 plus 1.62 log of L over epsilon to the minus 2.5. So I have a hydrofoil, again, English units, everybody loves them. 1.2 feet long and a width of 6 feet moving in seawater. 1.99 slugs per cubic foot, 1.1 10 minus 5 feet squared per second at 40 feet per second. Estimate the boundary layer thickness at the trailing edge. Estimate drag if the surface is rough. So the Reynolds number is going to be this 4 million, 4.4 million. Flow is turbulent. Transition, again, usually at 5 times 10 to the 5th. So delta over L, 0.16 over Reynolds number to 1/7, 0.16, 4.36 times 10 to the 6 to the 1/7, 0.18. Okay, not very thick. Delta, in this case, will be, yeah, I said 1.2 feet, is 1.2 times 0.018, which is equal to 0.0216 feet. All right, so I have 0.216, 0.0216, 0.24 inches, so about a quarter inch. C sub D, 1.89 plus 1.62 log of L over epsilon, that's 3,000. And that's all to the minus 2.5, 0.00644. Drag is CD times 1/2 rho u squared and the cross-sectional area. And that will be 0.0064, 0.5, 1.99, 40 squared times 6 times 1.2. So density, the value that I calculated for C sub D, density, velocity squared, and cross-sectional area of the plate in the water. And that ends up being 148 pound force. Any questions? You can do a lot of different examples with this, and one of the things I'm trying to do here is just apply these ideas and see where you can go with them. Derive modified forms of the laminar boundary layer equation for flow along the outside of a circular cylinder of constant radius r. And you have two cases to consider, which is that the boundary layer thickness is much, much smaller than r, and that will allow simplification. And then another one where it's about the scale of the radius of this. And r is just the radius of this pipe or cylinder. I guess it's not necessarily a pipe. And there you go. So for Navier-Stokes in cylindrical coordinates, and this is a great time to look at the appendix, in the book, Appendix D. And they changed the form of the equations. And one of them is that v theta is going to be in there. So theta is going to be the radial velocity, or the angular velocity of this. R is out, and Z is going to be in that direction streamwise. So you end up with v theta equal to 0, and del theta is equal to 0. So we are going to look at only one line. So we're going to take a 2D slice of this and not worry about how this is happening all around it, because we assume it's not changing as it moves around. VR is much less than u. That, again, is one of those assumptions that you depend on when you do boundary layer equations. The R momentum equation simplifies drastically. Del P del R is equal to 0, and P is only a function of x. And for a long straight cylinder, P is equal to a constant. So if that's the case, you end up with another form of the equation. And that's the equation. Again, if you go to Appendix D, you'll see it also there. And the 1 over to R term is actually crucial to this. You can't just write del R VR, because it won't make sense. It doesn't work. But for continuity, you end up with del U del X plus 1 over R del R RVR, which equals to 0. We don't have to worry about theta because it's equal to 0. So in continuity, it's not playing a role. X momentum with del P del X equal to 0 then depends only on the convective terms and the shearing terms over here. And essentially, it's going to be the same. Oh, no, sorry. Ugh. Right. There we go. Okay, yes. So for a very thin boundary layer, it's basically the same as the flat plate solution. We don't have to worry about much because R is acting in the y direction and X is essentially the streamwise direction. So the equations behave exactly the same as they have before. And all you have to do excuse me, is rewrite them, because that boundary layer thickness is so small, it doesn't play a big role. So 1 over R curvature effects. So so you can write del U del X, del VR del Y is equal to 0. Rho del U del X, rho VR del U del Y is equal to approximately mu del squared U del Y squared. And we have done this as a simplification and a translation from one coordinate system, R theta, to another, R theta Z, excuse me. And this one is just going to be XY, because in this case, it's not really affected by the curvature of the cylinder. Ugh. Did I not? I think yeah, oh wait, sorry. That's where I made a mistake. This is the thick boundary layer, and you do have to worry about the boundary layer thickness. And the thick boundary layer is affected by the cylindrical coordinates. Sorry, I should have been more clear on that. I did case B instead of A first. And so delta is going to be about the same scale, and we cannot make the simplifications for geometry that we can make in the second case. So in the second case, nothing's really there. It's just really the curvature is not playing a role. Here, the curvature is playing a role. I guess we're going to continue with that. Show that the following 2D laminar flow pattern with del P, or dP dx is equal to 0 is an exact solution for this. So u is given as u equals u naught, 1 minus e to the cy, and v equals v naught, which is less than 0. Find the constant c and interpret the flow physically. Okay. So So if you do that, then you have to calculate all of the gradients that are there, del u, del x, del u, del y, del u, second partial on u with respect to y. And so you can do that, and you end up with del u, del x equal to 0, del u, del y equals minus u naught c e to the cy, and finally del squared u, del y squared, which is equal to minus u naught c squared e to the cy. Substituting those terms in, you get rho 0 plus rho v naught minus u naught c e cy equals mu minus u naught c squared e cy, rho v naught equals mu c, and c is equal to rho v naught over mu. So just substituting in terms, you've got a solution here. You have to do two derivatives, and everything sort of works out at the end. You end up with an equality because both of those terms sort of appear. You don't have to combine anything with del u, del x in this particular case. And del u, del x, again, not a very large number generally in boundary layers, 1, 2.
Could you quickly explain where the rows came from in the substitution part?
Yeah, just a second. I should go back. Right there. So in my case, for example, in what I just did, this goes away to 0, this goes away to 0, and that last term is the only thing there. Go ahead. Was that the same question?
So for the slide that you were on before, what exactly is C supposed to represent?
It's just a constant. So it represents the velocity field, and it would here it would sort of give you an idea of how that changes. So this is a logarithmic value, and one of the things that is kind of important, you'll notice C is negative. This means that this number is dropping below 1. So this 1 minus e to the cy is always going to be smaller and smaller. And which kind of makes sense when you think about it, because you want that number to be as close to 0 at the edge and very large at the bottom. And at y equals 0, it's 1. So the vertical velocity is constant and negative, and it represents suction through a porous wall. So if you do graduate school, one of the things that you'll be stuck doing is a solution for a boundary layer over a porous wall. It's something that they have done for 100 years since Blasius graced us with solutions. And the suction provides a boundary layer from growing indefinitely. And what it does is essentially, as the flow goes over, it's being pulled down. It creates an asymptotic suction profile where thickness is constant, and delta is going to equal minus 4.6 mu over rho v naught. Any other questions on this one? So, is fully developed parallel flow or laminar flow between parallel plates an exact solution to the boundary layer equations? In what sense are boundary layer and duct flows the same? So if you go through and calculate the exact solution, which is for a Poisson flow, you get del P del X times mu squared, or h squared over 2 mu, 1 minus y squared over h. And if you substitute that in, to your equation, you end up with a couple terms that sort of disappear. So this one is 0. Duct flows don't change with downstream distance. This one is 0. They don't have any sort of change in there. And so you end up with del u squared del y squared is equal to a constant, which is that dp dx, which we know is a constant from boundary layer approaches. And so for the boundary layer equations, it ends up being essentially that minus dp dx plus dp dx is equal to 0, and there you go. Because mu del squared u del y squared is equal to dp dx. So it's a So is it a physical or an exact solution? Yes, it is. It's a boundary layer flow where the flares from the top and bottom wall have merged. Free stream is the center line velocity u max. Boundary layer does not grow because it's physically constrained by the two walls. And the entire duct is essentially one large boundary layer. And that's been the simplification we've depended on for years to make all of this work. So I have fluid flow along a flat plate, location where the boundary layer becomes turbulent. Reynolds number critical is 500,000, air, water, glycerin. And so transition will occur at x location if we take the Reynolds number, u times x over v, and we can just rewrite it as 5 times 10 to the 5th divided by 10, or 5 times 10 to the 4th times nu. So if you substitute all of the values, you'll notice that these higher kinematic viscosity terms stabilize that boundary layer. So glycerin takes a long time to develop versus water, which is pretty much at critical value within half a foot, so 7 inches. 8 feet is a bit downstream, but air is going to take a little bit longer. Everything depends on kinematic viscosity. So 0.605 feet, 8 feet, 650 feet for all 3 cases. And it's important to sort of get a physical feel for that. The fact that air, water, and well, maybe not glycerin, but how air and water will change how you have a transition point. I'm going to do one more example. Let's see. We got turbulent flow, 1/7 power law. And again, the 1/7 power law has been a pretty good fit for most data. And we have empirical shear, which is 0.0225 rho u squared nu over u delta to the 1/4, or inverse Reynolds number based on delta. And you're asked to find delta x and shear stress at the wall. So the momentum thickness and you can calculate from that the momentum thickness, just substituting in with that expression that we started the lecture off with. Second slide. And if you just substitute the expression, you end up with that. That expression is the one they gave you at the very beginning for the shear stress at the wall. Separating out the variables, delta to the 1/4 d delta equals 0.231 nu over u to the 1/4, I'm going to get it, dx. You end up with delta over x, which is equal to 0.37 over Reynolds number to the x to the 1/5. Substituting it in, you get tau at the wall over 1/2 rho u squared, which is 0.058. Reynolds number based on x to the 1/5. Any questions? A lot of this, at this point, there's a lot of just mechanical or mathematical operation. It's really recognizing what equations apply when, turbulence versus laminar, and also what the relationships are that you have available to you, and recognizing that library. Any questions at all? Ooh. I know you like this. We have currently 5 people who have done an evaluation, and lots of you have have your computers here. And it would be very nice, if you don't mind, to please complete the evaluation. I will step out as soon as I give you the QR code, and that you confirm. I am very pushy. And it's valuable. It helps me. I do try and do some changes to the notes already this year based on what you've presented, or what I've presented and how it's been sort of responded to, but it helps me. So Lex 0102, there you go. Anybody having any problems with the QR codes? You have 5 minutes before you have to go anywhere. So if you could complete it, that would be great. Thank you very much.